Hi everyone, I'm Alice Angry from AusIMM in Melbourne, Australia. I'd like to thank everyone for a live webinar today and those who are viewing this recorded webinar. This webinar has been organised by the AusIMM Social and Environment Society. So we'll now start the webinar. Over to you, David.
Thanks. So yeah, I'm displaying now. I'll go to, let's see if hopefully this works. Hello everyone. Thanks for joining in. So the reason for this was I met some IMM members at an event not a few months ago, and they were talking about the importance of tailings failures, and when we talked about a potential topic, and we kind of formulated this for the closure group because I understand this is the group of people most interested in the closure aspects. So it's to do with mechanisms of failure, or relevant mechanisms that still need to be considered after a tailings storage facility, or TSF, is either closed or fallow, or not having deposition. This title slide right here is that's actually the Pinto Valley failure that happened in the late 90s in Arizona on what was a closed TSF that was closure works were happening on. In that case, waste rock being placed on top as a cover. So it's not unprecedented that this can happen. Now the real reason we're talking about it today, and that it's come to the focus today, is that the failure that happened in January this year in Brazil was a fallow TSF at the time of failure, and had been fallow for about 3 years. So that is something that I'm not sure. I mean, a lot of people are aware there's a failure has happened. I'm sure some of those are aware that it was, there was an active deposition happening at the time. But that's interesting in a sense, because I think there's certainly a preconception, which is usually right, that once deposition stops and once things start to drain down or dry, things get safer, and that is generally the case. But there are still plausible mechanisms that can occur. Now, with respect to the failure in Brazil, probably a lot of you have seen this video, but I just included it for those who haven't, and it's always worth watching again because, oops, sorry. It's one of those ones, it's an unbelievable video in a number of ways. The thing I want to draw your attention to is, separate of it being fallow, is that when you look at that video, there's no perceptible change until almost instantaneous failure. That's, even though the report on what's happened to this TSF isn't out yet, everyone seems to agree that it was a static liquefaction failure. What the panel is going to be investigating is what was a trigger. That's probably their main focus, is what caused that to happen at that particular time. And I don't want to get into that because it's just speculation until all the data is out there. But the important thing to note is, this thing is looking, prior to it moving, there's very little externally visual evidence that it's about to happen. And that's what happens with very brittle, loose, saturated tailings when instability occurs. It can be very quickly, it can be very quick, and there can be very little warning. And that's important for a number of reasons, because I guess a lot of the things we talk about in terms of risk control is, monitoring, daily inspections, walking over the TSF, which is great and useful, but not all failure mechanisms are going to be detectable a day before because of cracking. And it can be a relatively small event that can take something like this TSF we're looking at here, that was already potentially in a very bad state. That final event that can cause this to happen doesn't have to be that big. The reason that's the case is because of events that have happened over the past 10 years, for example, but that last event that causes it can be quite small. And that's particularly important to think about in a closure context where, we might have a fallow TSF, and the things that we're doing to them in a closure work sense often are relatively small. But if unbeknownst to the closure team or to the people in that situation, if it was already in a very delicate situation, even those small types of closure activities could be enough in some cases. So, but going back a step, I think it's fair to say there's a perception that when a TSF stops deposition, drain down things start, drying starts, that it generally gets safer. And that is correct, almost universally. But even if those things are happening, there's still plausible failure mechanisms that remain, even after it started to drain down a little bit or dry a little bit on the surface. And it's quite possible that something that was, because of the way it was maybe designed or operated or whatever, was pretty close, could have been very close to failure on the last day they turned the spigots off. And 2 years later, things might not be that much better. So maybe it's 5% safer, but it might have been in really close to the line already. And when we see the number of tailings failures happening, it's not, there clearly are probably a minority, but a not unappreciable minority of tailings dams that might be in this situation. So we need to be careful whenever we start being responsible for changing things to a TSF. So today, what I want to talk about is just a really high level background on some of the relevant soil mechanics principles that I think you need to be across in order to kind of understand how these things happen. I understand the group isn't geotechnical engineers, so I'll do it as high level as I can, but hopefully it's of interest for you when you're trying to read about what's happened on these things. And then I want to discuss the types of rates of drain down we could see on some fallow TSFs by looking at just some very conceptual models of what drain down would look like, which can be quite slow. I'm sure many of you who've done this, been involved in the seepage modeling side or monitoring of a closed TSF will be aware of that. Then I want to examine some case histories, some of which are closed TSFs, and a couple are, or at least one is not a closed TSF, but what happened there could still be relevant to a potentially closed or fallow TSF. Discuss the failure mechanism, summarize what we see in those case histories, and then just some thoughts on what I think you'd want to look for coming at this from a closure works perspective. Like what kind of things to think about at a high level that you want to make sure have been done. But I don't want to just be a panic monger and try to suggest that every single tailings dam and in this case every single fallow tailings dam TSF is about to fail, because that's really not the case. So that I'm not saying that at all, but I'm just saying clearly we all would agree we need to be sure we know what the situation is in the ones that we're working on is the real message. Just to go just a really high level discussion on just how soils and tailings behave. They're what we would call frictional materials. And by that I mean that their strength is a function of the stress acting on them. So the more stress that's on them, the more shear strength you have. And the relationship, the way to, in a simplified sense, the way to link those two is what we call a friction angle. And you can measure a friction angle of a sandpaper block on a desk. You apply a vertical stress by putting a weight on top of it or using your hand even, and then try to move it. And you'll find that there's usually a near linear relationship between the amount of stress you have to put on the top and then the amount of stress acting down, and then how much stress you need to apply sideways to make it move. And that is what we call the friction angle, that linkage. And so different grades of sandpaper have a different friction angle. A really coarse grade of sandpaper on a rough desk is going to take more shear stress to move under all else being equal. And that's what we mean by frictional strength. It's not like concrete, for example, or steel. We don't normally think about how much stress is acting on the steel beam in a confining sense, usually in terms of how much tensile strength it might have or compressive strength. A steel beam is a steel beam generally. With soils, it's very much how much stress they're under is how strong they are. So if things that reduce the stress can therefore make them less strong, which can be dangerous. Similar to different grades of sandpaper, different types of tailings, different types of soils have different frictional strengths. Maybe your sand might be your beach sand's probably in the low 30s, 30 degrees. An angular gravel material could be 45, and anywhere in there. A clay can be in the low 20s, and tailings usually fall in the, well, it depends on the tailings, but they're usually, you don't get many 20-degree friction angles in tailings. Usually they're a bit more angular because of the fact that they've been more recently created and potentially broken down. So there might be more angular often than a natural sediment that's had time to be eroded or rounded. So in general, the friction angles might be a bit higher on tailings, but that's not the main point. The main point to get across with soils is, yes, they're frictional and their shear stress is controlled by the stress acting on them. But for soils and tailings, it's the effective stress that governs, not the total stress. So effective stress in soil mechanics is the vertical stress acting on that sandpaper block from gravity minus whatever water pressure might exist in between the sandpaper and the desk that might be acting in there. Now, in the sandpaper desk analogy, it's hard. You'd have to really contort this to be able to put water pressure into that situation. In a soil 20 meters below the surface, clearly it's going to have water pressure acting on it of varying amounts depending on where the phreatic surface is. So what happens is the water pressure, the higher it is, the harder it is for the particles to touch each other and to put pressure on each other. and that reduces the effective stress, which reduces their frictional strength. So they're frictional materials, but water gets in the way would be a way to describe it. And the more water gets in the way, or the higher the pressure of it, the lower the strength is. And so things that cause that can be very dangerous for tailings dams. So water is the key, which I'm sure you're aware of, and it's the key in a whole bunch of different ways, not just geotechnical behavior, but it's a key in this as well. So that's why when you look at plots like these schematic type plots of shear stress versus in this case vertical stress, it's vertical effective stress that you'll see in soil mechanics being used, and that's what matters, the effective stress. The water pressure makes a big difference in terms of the mobilized shear strength that you can get. So it's important then to think about what is going to cause those pore pressures, the water pressure that prevents strength to exist inside of our tailings. And Vic, who's written a lot of great stuff on tailings, he summarized it nicely into three kind of broad categories. Number one, which is probably the most intuitive and I think everyone will be aware of, is a high phoretic surface. So the higher the phoretic surface in a tailings or a soil or deposit, the higher the water pressure at a given depth, and therefore the lower effective stress in that particular element of soil, which means lower strength. Another one that's probably quite intuitive is rapid placement of fill or a cover or a next wall raise on top of underlying tailings. That load, that instantaneous loading, can produce additional pressures in the soil and the water, or in the water, that are above those that you would assume if you just calculated what they should be based on the phoretic surface. So we call that a form of excess pore pressure. And that's pretty well understood, I think, at least in geotechnical community. Number three is the trickiest one. And I'll be honest, a lot of people working even in tailings struggle with this one, and that's shear-induced pore pressure. That is the process of the particles being sheared in itself causes them to collapse and increase pore pressure. This is almost certainly what you're going to see has documented in the failure for that happened in Brazil. You see this every tailings failure that is geotechnical. You see this occur. Loose tailings, when sheared, collapse, try to reduce in volume, and the pore pressure goes up. So I'll show schematics to explain that, but that's usually the most risky and the one that happens fastest. Now, the high phoretic surface one is, again, probably the most intuitive. I think everyone, even if you're not a geotech, but you're in this area, you're aware, high phoretic surface is bad, low phoretic surface is good, generally. So looking at a really rough schematic of an upstream raised TSF, and let's say we're looking at this element of tailings here, and we're worried about it from a stability point of view, like that element of tailings, the strength that it has might control whether this slope is stable or not. Well, if we have phoretic surface 1, the effective stress acting on here is less because the water pressure is greater. So this whole system is more risky with phoretic surface 1 than with phoretic surface 2. So that's I think straightforward. What's interesting is if you have this slope and it's not in great shape, and you go from phoretic surface 2 to phoretic surface 1, the reduction that causes in itself can trigger a failure. And that rise can be slow. There's the misconception that it has to be some kind of rapid event. This could gradually rise over a year. And if at the point, when it gets to this point, things are not stable, the failure will occur. And there might not be that much warning depending on the type of tailings. So phoretic surface is key. Again, this is why almost certainly closed or fallow TSFs are considered safer, because usually you're going to be moving from 1 to 2. But the key questions we'll talk about later are how long is that going to take? Because that might, it can take a long time in certain materials. Now, excess pore pressures are what we use the term to describe pore pressures that are higher than you would calculate based on the location of the phoretic surface. Because if you know the location of the phoretic surface, you would say, okay, this element of tailings here is 10 meters below it. So it's 10 times 9.81 is, and that's how you calculate pore pressures, 98 kPa. But if you, for example, load this quickly by placing a bunch of waste rock here in a hurry, or building a wall raise or whatever else, even the tailings being deposited really quickly, that means that below that, the water, what happens in soil is the water bears the load initially. If you load something very quickly, it's water that bears the load, not the soil, and therefore the water pore pressure goes up. The water can't get away fast enough to dissipate that excess pore pressure. So clearly, if we start doing things like this, putting something there rapidly, it could then increase the pore pressures in here beyond what we think they are, which again can be a trigger for failure. So that's something to keep in mind, because this now we're getting towards things in particular that become relevant potentially to when you're closing a TSF. The key question then is the tailing still saturated? Because if it isn't, putting that load there might not be as much of an issue, because it can't generate water pressure anyway, because the tailings aren't even wet in the first place. But that's another discussion for a few slides. Now, shear-induced pore pressure, it's really important to understand what causes this, because it's so relevant to tailings, and it's hard to understand a lot of the failures, I think, if you don't really have a bit of a high-level understanding of this. Let's just imagine just another one of these PowerPoint schematics of an element of soil in some sort of lab device that lets us shear it. It doesn't really matter. We don't need to get in the nitty-gritty of lab testing. And we load it up, we put it under 100 kPa of vertical stress. And let's just say, for example, this one doesn't have any water in it. So we're able, pore pressure is not going to build up, and it can change volume because air is compressible. So if this sample wants to change volume, it can do so. Let's apply a shear stress to this. Let's simulate what happens to it below the slope of a tailings when it's loaded, and let's shear it. Now, what's really important is that if this tailings are loose, and I've tried to draw these silly schematic particles in like a loose arrangement, if they're loose, what happens is when shearing involves them trying to move across each other and distort somewhat, loose soils, when you do that to them, will try to get denser. Because the moment you start disturbing the structure, if it's already loose, they start to find a more efficient packing arrangement, which is fine, and it's good in a way that it gets denser if you can do this without pore pressure. So if you have this sample that's able to change volume freely without any issue, it will get, as you shear it, it will get denser. Okay, we call that in soil mechanics contraction. And the thing about it is loose samples do this. So loose materials do this. If you take the same material here on the left and compacted it very densely, it would actually increase in volume, because in order to shear, the particles need to move over each other and get bigger. But that's, unfortunately for us, tailings are rarely in that condition. They're hydraulically deposited materials are almost always contractive to some degree. Even filter tailings, if they're not compacted, are contractive. They're loose, I should say. They might not be saturated under most conditions if they were deposited dry enough, but they're usually loose if they're not compacted. So most of the materials we're looking at are going to be contractive. So this could play a role for us. We have to be careful about. Take the same element of soil, same condition, same lab test, everything. Let's fill it with water, and let's make this lab device a type of device where we can seal it. So we won't allow water to enter or leave the system, and it's fully saturated. Now, if we do that same thing, if we try to shear this element of soil, but it's full of water, the water can't go anywhere. So it's what we call undrained. The volume can't change. So the particles want to get closer together. That's what they want to do as it's being disturbed, but they're unable to because the water is in the way. It can't go anywhere. So what happens is the water bears the load, and that causes the water pressure to go up. In some cases, incredibly high amounts, to the point where the sample is almost liquefied. And that's what liquefaction really is. In the simplest way to describe it is some disturbance happens to this element of soil. The particles try to get closer together in a hurry. They can't do so because the water's in the way. The water pressure spikes. And if water pressure spikes, the effective stress goes down and the strength of the soil goes down. And that's the simplest way to describe static liquefaction, which is a very common failure mechanism. When you do, again, not to get into the nitty-gritty of lab testing, but just to show you qualitatively what it looks like, if red is the behavior of a soil where we start shearing it in the lab in this element of soil that looks just like this, with the valve closed, what happens is the shear stress builds up, and then it reaches a point, what we call the peak strength, where these particles eventually, or at that point, really want to start getting closer together. They've been disturbed to the point where they really want to contract. They're not allowed to because the sample's sealed. The pore pressures inside this lab test go way up, and the shear stress that we get out because of that drops drastically. So in this case, you had a peak of, I don't know, low 50s, a residual of maybe 6. So you've lost almost 10 times your strength just by a very, very small disturbance of trying to shear it, which could be, if it was in a tenuous situation, building that last small wall raise. That could be what pushes you to this peak. That's why we have to be very careful. And it goes from the peak strength to the residual quite quickly. So that's one of the reasons you often won't see evidence of a failure in some of these brittle failures, or sorry, evidence before it fails that it's going to fail. is because it's such a brittle process. So as this same test is running, we're recording pore pressure, and we see that the excess pore pressure inside that sample has gone up to 490 kPa. So it's lost almost all of its effective stress, which is the reason it's lost its strength, because without effective stress, the particles can't act on each other in a frictional manner. So it's losing its strength. So this is the simplest way to describe static liquefaction, which is really what we want to be very careful about when we're disturbing or changing tailings that we don't know the condition of, that could be loose and saturated. Because this, placing that last wall raise, or whatever the case may be, disturbing it in that sense, could be what pushes you over the top of that peak, and then causes you to lose that strength. When that happens, that's why things flow. You can imagine if all of a sudden something's happened in this tailings dam that's caused an element of soil to exceed that peak, and all of a sudden lose 90% of its strength, it's going to have to move a very great distance to reach an equilibrium again, which means you have what we call a flow event. So that's fast moving, brittle, little warning, and a great distance of travel, which is clearly a very dangerous combination. Now, everything I've talked about so far is implicit on the sample being either saturated, or sorry, the tailings or the material under question being either saturated or very, very close to saturation. But if we remove the water or significantly reduce the water pressure, things immediately get better. And that's what we talk about with, how a fallow TSF or closed TSF is usually getting safer, and it almost always is. But the question then becomes, if we turn off the spigots today, how many years is it until we see really important, improvements? And that's not the easiest question to answer. I'm sure many of you have been involved in, seepage predictions of these things, and it's not actually the easiest thing to predict, I think. And I've been involved in a number of fallow TSFs where we've gone back 10 years later and there's been a phreatic surface, well, higher than we would have wanted it to be, and much higher than I think probably everybody would have thumbsucked, at the time. Just to give a very simplified approach to just to quantify what kind of time numbers we're looking at here, I've just made a simple column model with two, arbitrary but reasonable tailings strengths, permeabilities, and what you would call soil water characteristic curves, or unsaturated soil characteristics. One I've taken to be something on the sandy silt side, so maybe your gold tailings near the perimeter where it's segregated a bit and it's sandy silt. The other one on the other extreme being maybe your clay tailings, maybe your iron ore, some of the clay-rich iron ore tailings, or maybe some bauxite residue or alumina residue perhaps getting up there. So this to me is kind of a rough span of a lot of the tailings we would be dealing with in Australia, I think. That covers just a bit of a broad range of that, just to look at two scenarios here. So let's just for argument's sake, just for discussion, let's take a 50-meter high column of that tailings, of both types, and let's say that we turn the spigots off, and the water, we had a really good drainage system and it can drain out the base freely. Now that in itself is probably that's a non-conservative assumption, because a lot of the cases we're going to be sitting on top of another 20 meters of some kind of clay material perhaps, which makes everything that we're talking about now worse. But just for argument's sake, let's assume it can drain freely from the base. It's either a sand foundation or there was a good sand drain in the bottom. Now let's, again, just assume initially that there was a hydrostatic profile, which is the orange dots here, which I guess isn't completely consistent with it having a nice draining bottom, but it's not impossible. It's just easier for the schematic. And let's say for the clay tailings, we leave it to drain down for 10 years and then 50 years. Okay. What you see is that the pore pressures become negative, which is great, because that means it's probably desaturating to some degree, and or it's stronger anyway, because negative pore pressures are better than positive pore pressures for strength. So that's good. Okay, it is draining down. But what we see is, because of material like a clay, like if you're getting into the clay end of the spectrum here, yeah, sure, negative pore pressures start to develop, but that doesn't mean that it's become highly unsaturated, in the sense that there still could be almost, in a lot of the tailings, the pores are still almost entirely filled with water, because clays take a very, very long time to drain down and to lose that water. And they never lose at all. Clays actually hold on to, or almost never lose all of it. They always hold on to their residual water content. So in this case, and sorry, this whole schematic or assumption, scenario is assuming no recharge. There's no new water being dumped on top, which again is non-conservative, but easier for the discussion. So yes, this tailings dam is much safer, much safer. At 10 years fallow, it's much safer, but it's still potentially very close to saturation. So if we go and start throwing a bunch of rock on top of this thing, that could generate pore pressures, because if you're 98% saturated and you throw a bunch of waste rock on top of it, it will become saturated and pore pressures will generate. So that's and again, this is a if it wasn't clay, if it wasn't free draining at the bottom, this would be worse. Because when I first put this schematic together, it didn't make any sense to me or this scenario, because I know I've been involved in TSFs that are still very saturated after 10 years, but that's because this is a free draining scenario, whereas that one was not. If you switch to the sand silt tailings, things are better. And in this case, if you're free draining on the bottom of a sand silt tailings, you're probably getting after 10 years to a point where, yeah, even if you did throw waste rock on top of that, it's not going to generate pore pressure, which is good, because that means stability is better, things are better. Now, turning to Brazil, in that particular situation, it's a much wetter climate than we often deal with, or in a lot of parts of Australia would deal with. So this scenario, this model is nonsense for that one, because it's constantly being recharged by wet seasons. So it's not going to drain down anywhere as efficiently as this. And there's been published data showing that it still had a pretty significant phreatic surface in it 3 years later. So maybe this is just a kind of great discussion on just the time scales we're looking at here. Even in a situation where everything's perfect, where you have a sand drain at the bottom and no recharge, you're still, your clay into your spectrum is going to be almost fully saturated, even 10 years later. So the water things get better, but they don't get better to the point we don't have to worry about stability. I guess I've already kind of just covered this discussion topic. And it's worth noting that I'm not sure, maybe everyone's aware of this, but very often the initial tailings that are deposited are more clay than the ones that are deposited at the last 5 or 10 meters, because if in many types of deposits you're getting into the fresher rock as you get deeper. So if you're going to be studying this problem and taking samples to study this problem, you might want to be looking at the stuff from depth, because if you just grab a bag of sample from the beach, it may not be as representative of 20, 30 meters down as you'd want it to be in a non-conservative way. We have the technology, I'm sure a lot of you worked in this, to model this and look at all these scenarios. It just requires some relatively good types of lab testing and a relatively comprehensive type of model to deal with, or to understand what's going to happen. So with a little bit of I guess geotechnical background there, for if that was of use for anyone, I just want to talk about some TSFs, some of which and one non-TSF, some of which were closed at the time of their failure, and one was not, but is close to home and is quite relevant because of what was enough to trigger the failure there. So Semergo in South Africa, which is an interesting closed TSF failure, or just recommissioned. Pinto Valley, which is a kind of a classic one because they were doing closure works on it. Cadia, which I'm sure everyone's familiar with, but I'm not sure how much you've seen about what the panel feels was the actual trigger mechanism of that failure, and how it wasn't really that much. What was happening to it at the time that might have pushed it over the edge wasn't that much, and it had been a case where things have been building up for a while. I think there's evidence to suggest that. So that's interesting, because again, the things they were doing at Cadia weren't enormously different to what you'd be doing in some closure applications in terms of the disturbance happening at the last second. Mary Spray in South Africa is interesting, and it was closed at the time. Now, sure, they were doing insane things about still putting water into it in a very bad way, but it was a closed TSF. There wasn't rapid rise happening anymore. And finally, these lignite mines in Germany, closed coal deposits, which I'm not sure how familiar you are with them, but they're very interesting case history. Again, talking about a closure situation with this kind of static liquefaction occurring. So Semergo is very interesting in that it kind of draws upon those seepage models a little bit, in that it was an upstream raised TSF in a pretty arid environment in South Africa, and it had been fallow for 20 years at the time the failure happened. There were no pore pressures in the tailings based on piezometers. They drained down in the sense that there wasn't a hydrostatic profile, but they were very, very close to saturation. So very similar to one of those models showed earlier. They wanted to hydraulically remine the TSF, and as part of that, in one of the areas, they were storing some slurry on top of the tailings dam. This was enough to trigger rapid resaturation of the tailings and failure, I think, only a couple months after they started this process. This is about 1 month. This is a schematic of the pre-failure and post-failure shape in this area. And blue, I've highlighted blue. These figures are from Blight's textbook. Blue is highlighting where the phreatic surface was at the start of this 1 month of new deposition, and that's where it is maybe 25 meters higher after 1 month. So after only 1 month of placing some new tailings on top of this thing, the phreatic surface has risen 25 meters. Now, the only way that could happen is if this tailings were extremely close to saturation and just needed that extra push to get them back saturated and then to start to rebuild up a profile like this. So this is clearly relevant, I think, to what can happen to a closed TSF if it got hit with a large rain event after closure, maybe bigger than it had experienced during the operational years. If we went back and started doing things to a TSF, a very, very relatively small change in events here was enough to cause this rapid increase in phreatic surface. So not to say that you couldn't do things like this, but you need to, if you understood the slope and had monitored properly and had all these controls in place, you would have known in advance and been able to deal with it. But we're talking here, I think this was the 90s, so probably the understanding wasn't there, and it was, it wasn't being looked at in the detail we should be looking at it now. But I think it's a really useful case history in this context. Pinto Valley is a really, really useful one. So this is a closed TSF, upstream raised in an arid environment. So this isn't, precipitation-wise, we're talking, this is quite relevant to some areas of Australia. I don't know how long it was closed. I haven't been able to figure out or find how much time between end of deposition and when they were doing what they were doing, which kind of is unfortunate because that's relevant in terms of how much it would have drained down. So a flow slide occurred down a river when they were placing waste rock on top of it as part of cover works. Now, throwing a whole bunch of waste rock on top of an upstream raised TSF probably would ring alarm bells regardless of whether the Brazil failure or what we understand about geotech engineering. But probably I would assume that there was the view that at the time that the tailings had time to drain down. But what appears to have happened here is that maybe they did drain down to some degree, but they might have still been very close to saturation. So again, if you put a 20-meter lift of waste rock in a rapid way on top of tailings that are at 99% saturation, then that's going to cause them to resaturate and potentially drive up their pore pressures. This is a photo of the failure looking kind of that way at it. So from the top of this hill, but from aerial. So that's the top of that hill, that's the failure area, and that's flowing down the river. So the waste rock had gotten, they covered most of the interior of the TSF. It was only in one of the first places they got near the edge that this happened. But again, that's not to suggest waste rock covering of a TSF isn't a great, or potentially, encapsulation isn't a good thing to do. All they needed to do was control maybe how thick the waste rock was, or how long they had to wait between placing it, or put some of it around the perimeter as a buttress, and then they would have been able to do this. It's not to say that encapsulation is bad or any of that, but just understanding the conditions in here would be critical if you're going to try to do this. There was no fatalities in this site, but it was pretty close from the look of this. This is the people working on those lifts right when the failure happened, or the vehicles. Just for references on that, I've had a couple of people send me some nice photos, particularly Lawrence Hansen of AMEC, who was involved in the rehabilitation. So I just want to acknowledge him for sharing those photos, which are above and beyond what you can find just in the few papers on it listed here. But again, just to come back to that early slide about things that can cause an increase in pore pressure in the tailings, they were doing exactly this schematic. They're putting a whole bunch of waste rock there quite quickly on what were tailings that were either saturated or very, very close to saturation, causes pore pressures to go up, strength to go down, which can be enough to push you over the edge. Now, I want to talk about CADIA. Now, CADIA was, everyone's probably in the mining industry is quite aware of this. Happened in March 2018. In many ways, I guess at the time it wouldn't have looked like that, but it was a lucky break in many ways. No fatalities. They had a pit to go to, so it could have been, it could have been worse, I guess. It raised a lot of awareness, and it could have been worse. But of course, the North TSF that failed here was an active TSF. So how does this fit in the context of a closure discussion? Well, it's worth what the panel thinks triggered this is very interesting to think about in the context of closure works. So this is a section I've drawn over, like, by digitizing one of the figures in the panel report. And actually, Newcrest has been very nice about letting me use their images from the report in presentations, which is not always the case, because sometimes these panel reports get a lot of very confidential and stuff. But they've been very nice in sharing data. So this is the TSF right leading up to failure. That's dark brown is what was initially constructed as a large, I guess, more conventional downstream TSF. Orange are wall raises when it was converted to an upstream TSF. And this is the pink and the green are a core. Now the green foundation material, it turns out where it failed was a lot more clay rich than, I guess, the general view of or understanding of the site had been. So the particular area where it failed, this foundation here was a bit different to elsewhere. Now, what was happening essentially that the panel believes led it to trigger was two things. A buttress was being constructed in order to increase the safety of failure mechanisms acting through the tailings, which are generally going to be the worst ones. Usually it's not going to fail through a large engineered downstream dam. Also, in order to enable buttressing from the ground up, which is what would more conventionally be done, excavation was happening at the toe here of about 3 to 5 meters of tailings that had built up there, because this area is below here is kind of close to the other TSF, and there was some overflow material there, I understand from the report. So two things are happening here. A buttress is being constructed, and you're moving material at the toe. Now, in combination, that could potentially be an issue, as it appeared to be here. As it turns out, this more clay material, the panels inferred was, prior to these additional works happening, was already being weakened and shearing as a result of all the wall raises that had been built over the years. So things were already, not going great in this clay. So that means that these, what are relatively small additional disturbances, were enough to trigger a failure. They caused the clay to move to the left even more, which then caused, without getting into geomechanics, a type of extension stress path in the liquefaction and in tailings here, triggering liquefaction, and then that localized flow. Now, for closure, the thing I really want to focus here on is, if you come to a TSF, it's not unusual that closure works could consider things like cleaning drains or reshaping slopes or putting cover material on slopes. And so I just want to draw your attention to the fact that if one was unlucky and ended up doing those things to a TSF that was for no fault of your own, had historically been in a not great situation, then you don't want to be the one sitting there standing holding the bag that, we would just put a 1 meter cover zone on here. We just had to clean some drains at the toe. Well, you just want to be careful, I think, that you're not in a situation where that could be what does it. It would be the message, I think. Mary Sprout is, which I think I'm pronouncing it terribly, sorry if you're an Afrikaans speaker, but so it was an upstream raised TSF in South Africa, failed in 1994, and resulted in 17 deaths in the downstream, or the village that was downstream. And it's a sad kind of story that the original plan was to put the village on the other end, on the other side, and I think I can't remember why it got switched, or sorry, to put the TSF elsewhere because of where the process plant was going to go, but it got changed around in the last second. So the TSF failed. It was closed nominally at the time of failure, but it was still being used for water storage, which didn't help at all. And it had not, again, it was a TSF that had a whole bunch of problems through its life. In particular, where it failed was a bit of a low point, which had always had the most loose, saturated tailings at them. So this area was always, a potential area of risk. But there was no real tailings deposition happening when it failed. So it just shows it doesn't have to be that actively deposited to be a risk. It flowed up to 4 kilometers, again, quite quickly, and it took houses right off their foundation. It sheared them right off their foundation. This is an image, a satellite image of not too long before the failure. What's really interesting about this failure is it's the first time that I think things like satellite imagery were used in like an investigative sense, at least in tailings, because there was a big controversy over whether water was being stored on this fallow TSF or not. And some people were saying, no, we weren't storing water there, and some people saying they were. And they ended up being able to use what at the time was a quite novel way to get publicly available images to prove in the court proceedings that there had been water at the top on this the failed TSF, actually right up against the edge here. So what had been happening is, yeah, it was a closed TSF, but there was another TSF next to it, and they were using this one for storing some primarily additional water. And because of a long history of not good deposition and other problems, that water didn't really end up in the decant. There was a low point up against the crest, which is obviously not great for a number of reasons I'm sure we're all aware of. But in this case, a rain event occurred as well, which was enough to cause overtopping. There was not much freeboard in here. It caused overtopping, which then caused some erosion. So it's not the overtopping so much that's even though the overtopping is terrible and we would never want that to happen, it's what the overtopping did. Because the overtopping started, and then later in the night there was a loud noise came from the TSF, and then the flow through the village ended up being much stronger after these loud noises occurred. And this is something you hear a lot on these types of static liquefaction failures, is people, like eyewitnesses, will report like a banging noise or a really loud bang when they fail, and that's that brittle loss of strength happening inside of a tailings and when they release. That's another picture of just the size of the depression. It wasn't even that big of in terms of in the context of the whole TSF. The amount that discharged wasn't that high of a percentage. But the erosion, it's the erosion I want to draw your attention to as a trigger mechanism. I mean, overtopping is we would never want a dam to overtop in any circumstances, but it's what the overtopping did and actually how small of an erosion it needed to be to do it that's interesting. So this is an eyewitness. One of the eyewitnesses was an amateur artist apparently, and he drew this based on what he saw very soon before it actually flowed in earnest, because this overtopping had been happening for a while before it really released. And what it turns out is that area right behind where it overtopped is an area that, as I mentioned before, had been a low point, had water on it throughout most of the life of the TSF, and the tailings in there were particularly loose. So coming back to that idealized laboratory test, the material in there was that kind of stuff. It was very, very loose, because tailings that deposit, or silty tailings that deposit through water subaqueously, are usually the loosest and most dangerous. It's just that they just form a looser structure. So coming back to these very basic PowerPoint schematics of what was happening, you had a situation where it was already saturated. Despite being closed, this low point was already always saturated because of location of the pond. You then have a further rise in that standing water because of a rain event. Overtopping occurs, causing erosion, so chewing out about that toe in that area. Okay, this situation, this TSF was in such a situation that what is actually, especially when you consider 3D effects, not that big of an erosion event, was enough to start triggering liquefaction in the tailings behind. Because if you remove the toe, if you remove toe material, you're increasing the shear stress in there. It's like making this slope steeper, right? So if you have loose tailings that are already on the line, already really close to that brittle contracted behavior, and you all of a sudden take the toe away and increase their shear stress, that's a good way to trigger liquefaction. So Merisprit's reasonable for relevant for a number of reasons. Erosion is something we want to consider in closure works. Closure water management, something that's clearly quite important. And again, you got a situation where, yeah, sure, standing water is bad, erosion's bad, but to make it that particularly catastrophic event, you needed to have had a situation where things have been going bad for some time in terms of this whole area was always going to be a high risk area. So a few things combined, but all of which are relevant in a different way to, I guess, closure situation. These, no, it's funny, these rehabilitated coal mines, coal waste stockpiles in Germany are, for us in the tailings world, when Andy Free showed me these slides, because he'd found out about it at a mine closure conference in Europe, it was really interesting because we'd never heard about it in the tailings world. Maybe as closure people, maybe you're more familiar with these things. So these are Andy Free slides he's allowed me to use, so thanks to him. So apparently when East Germany, when Germany reunified, East Germany was the largest producer of lignite coal in the world. But I guess a lot of them were state-run enterprises, and once it all got exposed to the free market, a lot of those shut down, weren't economical. So production fell enormously. So you had a situation with a whole bunch of closed mines. And what happened is in some of these closed mines, what they were referring to in their literature as a ground break appeared, meaning a significant flow of material without any real warning, causing damage. And then they started happening at a greater frequency. And apparently there was a real lack of understanding of what was causing this. Now, apparently this is even worse in that a lot of the land, once these mines were closed and handed back, the land near the lakes was actually considered good real estate, and some building happened in that area. So it wasn't just failures, it was having effects on real estate and evacuations and these kind of things. There's now been more than 50. A paper that was in, I believe, a mine waste conference was talking about how some people working in the area didn't really understand geotechnically how this could be happening, and the fact that there was no real strong external trigger that they were aware of. They couldn't understand why that would happen if there wasn't a strong external trigger happening. I think we actually do have a geotechnical understanding to explain these, which I'll briefly show. But I think they're interesting because in a closure sense, even though they're not strictly tailings. So what was happening, to get into more detail, is a lot of the waste from these mines would end up back in pits, and it would be placed there very loose without compaction, which wouldn't be surprising for, why would you really compact it? It's a loose material. To enable mining to have occurred when things were active, there was a lot of dewatering happening, resulting in a depression of the groundwater level. So then you turn around and close all these mines. A lot of the dewatering works are going to stop, and the groundwater level starts to rebound back. But that causes, you might have areas in these pits or near these pits where you have waste stockpiles placed very loose, and all of a sudden now the pore pressures in them are increasing. Increasing pore pressure means reducing strength. And if you have these loose materials, they're the type of materials that can then exhibit contractive undrained shearing, contraction, increase in pore pressure above and beyond just the rise of phreatic surface. Sorry, that's a duplicate slide. I'll go to the next one. This is an example of, I guess, the effects of one of these events on real estate in the area when you start having these failures that occur and then propagate backwards progressively. So clearly a lot of evacuations occurred because of this. A lot of land a lot of real estates had to be, abandoned because of this. And some have been some of them have been quite large, even over 4 million cubic meters of flow, and some fatalities in some cases. Houses submerged, hundreds of meters to a kilometer of area, and they're quite quick, which is, again, there's little warning and they're quite quick, which is, again, very similar to how we see a loose tailings potentially fail. So we're looking at the same physics here, the same mechanisms. And this is a video, which hopefully works, of one of these, not one of the huge ones, but in an area where I think they knew there were already these problems happening. So let's see the video here. The person with the camera was probably starting to get concerned about now, but it doesn't get to that extent. But again, very little, not much happening before it starts to move. Maybe something, because he was pointing the camera at that exact spot, so I can't say there was no warning, but not much warning usually, and then relatively rapid and large quantities of material moving. So what could be happening in this image is if you've got a whole bunch of waste material that is been placed loose, so it's in a loose state, it's at risk of that contracted behavior, and all of a sudden you start, rising a pit lake because it's rebounding or even seasonal effects, that's reducing the effective stress inside some of that material. That reduction in effective stress reduces the strength, which can then cause that kind of brittle shear straining, which could lead to that exact behavior in that video. So again, it's water pressure is almost what always does it for us. It's the higher the water pressure, the more dangerous things are. Not a tailings dam here, but certainly I think of interest, if you weren't aware of these, I think from your closure perspective, as an interesting case history. Andy's been trying to get more information out of this actually because it's such an interesting case history, but he hasn't been that successful. So I don't know where they are. They must have done more work on this since then, to understand it and risk manage it. But I'm not personally that aware of what's happened. So just to kind of summarize the mechanisms that could trigger a failure, that it still exists after a TSF is closed, those could include things like a major rain event, which you could easily have a rain event a few years after a TSF closed that was bigger than anything that happened before. So it could actually put a closed TSF in a worse situation than it had ever experienced as far as water pressures go. So that's a good example, because if you have a 10-year, 20-year mine life, and then that TSF sits there for 50 years, and it's still close to saturation, and a lot of water gets dropped on top of it, you could then be in a worse situation than it had existed actually during deposition, even though it's fallow. If they're being used to store water, and/or storm events are happening, and now the infrastructure has been removed, and the plan is to leave water on top of it in some circumstances. If that water gets to a higher level than it had ever been, again, exact same issue. Things could be worse, even in a fallow situation, if a lot of water comes into play. And the types of earthworks that can be done that sometimes happen in a closure setting can be enough to trigger this if the TSF, owing to reasons that happened long before closure work started, was already in a delicate situation. It doesn't need to be, these things can be right on the line, and if they are right on the line, it wouldn't take very much to push them over that. Digging a drainage channel out at the toe as part of a closure situation increases the shear stress. Depending on how you're doing it, reshaping the slopes could cause a minor increase in shear stress. And placement of cover material, clearly, it depends on the amount, but the amount it would require to trigger a particular failure depends on the condition of the tailings dam. There's no rule that a 2-meter cover is okay and a 10-meter cover will cause failure. It depends on the geometry of the TSF, phreatic surface of the TSF, strength of the tailings, how loose they are. So it just requires that clear understanding of the tailings. So again, I guess just some important points is that, just to summarize the second level, is that just that fallow TSF could be really close to the edge of the line because of nothing that a closure team has done. So I guess, yeah, you just want to be careful that you don't put yourself in that situation. And water management, you just want to say water over and over again. I think everyone's aware of that, but for every reason, but certainly geotechnically, if you can get rid of the water pressures, you're in great shape. And I mean, that's why people are so keen on filter tailings, although it's not without its problems, because a lot of filter tailings don't end up as dry as we'd all wish they were or hope they would be in the design. So I'm aware of filter TSFs that definitely have saturated regions inside of them, without a doubt, that we've seen. I guess, and I'm a geotech engineer, so I don't want to talk up geotech engineering here, but yeah, good geotechnical advice and understanding of what's the situation of a closed TSF or fallow TSF is key if you're going to start changing it. And another point that's maybe looking at a different way is if the stability analyses, let's say there is a report on the TSF, right, saying that it's fine, but let's say it was done 15 years ago. I can almost guarantee that 15 years ago, the level of, I guess, rigor and conservatism being applied to tailing stability was less than it would be today. That's just the way the industry has moved. I mean, because of the failures that have been happening, there's a lot more understanding of these mechanisms. So 15 years ago, 10 years ago, it would probably not be as robust as it would be if it was done today. So that's important to remember if what you're relying on has been on a shelf for 20 years. And it's unfortunate, but loose, brittle tailings are very common in many TSFs. Placing material hydraulically is not the best way to get it dense, and therefore it's likely to be, if the materials are saturated, they're very likely to be loose. And a good understanding of phreatic conditions, and particularly how they're going to change over time, is the key for all of this. Because if you think it's going to take 50 years to drain down, or 10 or 5, that's going to really change your decision making, I think, on some of these things. I guess maybe I keep coming back to this, but I just wanted to kind of focus on a closure point of view, is that, yeah, if you're the closure person, you don't want to be the one that comes in there and puts a 1-meter cover on there and triggers it, because often people aren't going to talk then about how it would be badly managed for 30 years. Everyone's pointing at that last 1 meter of lift is what usually seems to happen. And again, coming back to the beginning, I don't want to at all suggest that any that high a percentage of closed TSFs are sitting there waiting to fail. But there clearly there is some percentage. I don't know what it is. It's low, but it's not zero. So you don't really want to start doing things unless you're sure you're not in that category, I would say, is maybe one way to say it. So that's the presentation for today. I just want to acknowledge my coworker, or my colleague, Professor Andy Furey, because he shared some slides on actually both Mary Street and the lignite mines. Lauren Hansen from AMEC, who shared some of those extra photos of Pinto Valley, and Bradley, Georgia, and Alice, and the AusIMM generally for just extending the invitation and helping set up, and they gave me some feedback on whether the slides were kind of, on point for closure people. So thanks very much. That's it. Yeah, questions.
David. Great presentation. We'll now open the floor to questions. So if anyone would like to ask David anything, you can just type it into the question box in your control panel and I'll read it out for you to answer. We do have a question for you, David. What things would we look for or see purely in a visual way when visiting a fallow TSF or reviewing high-level plans, sections that would give us some warning of risks?
Okay, just visually is hard because, well, I kind of come back to the beginning. So if you just visually is a bit hard because you wouldn't necessarily, cracking, I guess, is what things like cracking are probably what comes to people's minds in a geotechnical sense. And sure, if you see cracking, that's bad, but visually, it's really hard to say to yourself, okay, this is a real risk. So I wouldn't, reliance on visual is very problematic. But in general, I guess across the board, the steeper it is, all else being equal, the more dangerous it is. If it's an upstream raised TSF, there is more risk of the tailings or loose material being in a location where they could control stability. So that if they're saturated and if it's saturated still and it's an upstream raised TSF, those materials are more likely to be a risk. Downstream raised TSFs, if they've been downstream raised the whole life, a lot of these issues, there are still issues, but a lot of these main, like, liquefaction, brittle failure, start to drop away in that case. So yeah, like in the section, if you look at the section and there's a really thin upstream sheen of wall raises and it's quite steep and high, well, right away, that's an extra thing to worry about.
Perfect, thank you. Another question for you is there any impact of material transformation in a tailing?
By material transformation, do you mean like, I guess like a mineralogical or chemical change or degradation, or say chemical? That's an area that I know people are looking at, but I don't think, well, I can't speak really that well on it. I mean, I think if you have I know, for example, if you have tailings that are like alumina residue, so they got a pH of 13 or whatever it is that they go out there at, if it was conceivable that they were flushed through with rainwater to an extent, that would change the geotechnical properties for sure. Certainly, if you expose that kind of alumina residue and change its pH, things change. I'm not even sure off the top of my head for the better, for the worse, but it does change the properties. Turning to, I guess, it's still in the chemical realm, if you look at like, well, specifically the gold fields, but it could be elsewhere. I mean, the gold fields are a great example because it's 100. What's the pore fluid in those tailings is like 100 grams a liter or something like, can range from 50 to 200 even. Now I don't know how likely it is that a gold fields TSF would be flushed with enough water to change that. I don't know if I can really visualize that given the climate, but that I know for sure that changing the salt content will have a big effect on the geotechnical properties, and that in that case it makes it worse, without a doubt. If you take a tailings that was hypersaline or even saline, like 50 grams a liter, 30 grams a liter, if you thought that all of a sudden that salt content was going to go to like 1 or 0 or much lower, it will be less safe. It's to do with how clays I should go back a step. It will make it less safe if the material includes clay mineralogy, which is not that unreasonable in some of these conditions. This is the kind of problem that was actually first discovered in Norway, where the clays, some of the clays there were deposited in the ocean, in an ocean environment, and then I guess because the glaciers retreated and the land swelled up, so a lot of them have been above the sea level for 10,000 years or something, and that's enough time for them to flush and become less salty. So what happens is the structure of the clays that was formed under 35 grams a liter, but now it's say 5 or 0. That creates a situation where that clay is way more risky, is way more brittle, and is very dangerous. So if this is an area that actually we're doing research on right now, I have a master's student preparing a tailing sample with salt in it because it's something we're interested in, studying this effect of salt. Yeah, definitely. If you think it's possible that you're going to reduce the salt content in a TSF, that could make it worse. So that's hopefully that helps you.
Thanks, David. Another question is, what specific testing would you recommend to do prior commencing closure on a fallow TSF?
Okay, so let's assume this is an upstream TSF for the argument, maybe, because then we're focused on the tailings more so. If you have an upstream raised TSF and you want to start doing things to it, I mean, obviously you're going to want to start with the last geotech report, but let's say that you thought that was insufficient for the purpose of the question. Okay, the comb penetration test is certainly going to be the key to any one of these investigations. That's a type of test where you push a probe through the tailings. It's quite a productive test. It's really accurate, and it's the best screening level technique to find out, is it saturated still? Is it loose? What's the water pressure? All those things. So it's incredibly useful. So the CPT would be indispensable. Taking samples of the tailings in areas that are of concern, actually using the CPT rig equipment, which can then be modified to pull up material rather than probe it, is absolutely critical, because then, even though the CPT is a screening level tool, it's very hard to figure out everything just from how one probe load cell reads values. So usually you would do a suite of lab testing on the tailings, usually from depth of areas of relevance. And in a closure sense, you're going to want to probably be doing permeability testing, certainly soil water characteristic curve, if you're worried about drain down, things like that. And then if you're worried about liquefaction triggering, things like that, it's probably a bit, you could go on for 50 minutes. It's a bit beyond the scope, but it's things like measuring the critical state line, measuring the cyclic resistance, because I guess I didn't talk about earthquake loads much here, but earthquakes are just as relevant after the spigots are off as when they're on. So knowing like what magnitude of earthquake could be enough to trigger liquefaction, which could then control, how you reprofile the slope, or where you put buttresses or where you put covers. So that's the main, the CPT followed by a pretty good lab program on material from depth would be the main key. There are others, but that's certainly the most important one.
Great, thank you, David. I think I have time for one more question. What do you see as necessary for regulatory bodies to know information to collect prior to a site moving into a care and maintenance or closure phase, to ensure that regulatory bodies are aware of potential risks associated with the closed or fallow TSFs, and that these risks are managed by the mine operator?
So it was, what information does the regulator need? Was that the start of that? Sorry.
Yeah, well, what do you see as necessary for these bodies to know, or information to collect?
Yeah, okay. Well, I mean, I guess there's a lot there beyond geotech. There would be the information you would need in that case would be a plethora that would include way outside geotech. But if from speaking to my area, if you're a regulator and you want to be able to collect information to say this TSF isn't going to look like Pinto Valley, isn't going to do this, it's going to be, high quality geotechnical analyses of the stability of that structure. It's going to be that report and reports by a geotech consultant or people like that who have looked at the TSF, have analyzed it, done all those, the CPT in the lab and that work, shown that it's stable, shown that it's become more stable with time, looked at things like what happens if we get a storm event, or what happens if these things happen, like what if the toe erodes over 5,000 years, those kind of things, because you want it to be safe enough that those kind of things are not going to push you over the edge. I guess that's the main thing. I mean, there'd be a whole bunch of other things like erode, how's it going to erode over time? How the plume, is there going to be a plume of contamination? I mean, that's somewhat out of my area. I can't really talk to that. But yeah, just you're going to need to know that there was a solid geotech investigation, geotech analysis that proves that it's stable in a macro scale, like stable, like it doesn't do this, Pinto Valley stuff. Those reports aren't going to answer, is it going to erode over 10,000 years? That's a different type of study, which you also, I think, would need. But yeah, if that answers the question.
It does. Thank you very much, David. I think we might close the webinar there. So thank you very much for presenting. It was a very insightful presentation. And
thanks for everyone.
And thank you everyone for attending the live webinar today, and those who are viewing this recorded webinar. So thank you and have a lovely afternoon.
Thanks. See ya.